Good afternoon, everyone. Thank you, and welcome to our distinguished lecture series, the third one in this academic year. It's my pleasure to introduce Professor Jack Dongarra. He has a very distinguished career in the area of linear algebra, parallel computing, and the use of advanced computers, architectures, programming methodology, and the tool for parallel computation. He hosts appointments at the University of Tennessee, Oak Ridge National Labs, and also University of Manchester. He has a long list of honors and recognitions, including IEEE Seth Fenbach Award in 2004, and the recipient of the first IEEE Medal, Excellence in Scalable Computing in 2008, and the first recipient of a SIAM Special Interest Group on Supercomputing Award for Career Achievement, and IEEE IP DPS Charles Babbage Award in 2011, and ACM Ken Kennedy Award 2013. He's a fellow of AAS, ACM, IEEE, SIAM, and also a member of a National Academy of Engineering. But for us, that a lot of us know him as the man behind the top 500 supercomputing rankings, so that's a long-lasting impact to the society. Right, let's welcome Professor Dongarra.
Thank you for that kind introduction. Yeah, so I have a position at the University of Tennessee, which is located in Knoxville. I also hold an appointment at Oak Ridge National Laboratory. It's about maybe 40 kilometers from the Knoxville campus. And I have a position at Manchester, about 4,000 miles from Knoxville. I don't go there very often, but I do participate there. So I'd like to talk about high-performance computing and look at some of the events that are unfolding. I'd like to make this informal. So if you do have a question during the talk, ask it if things are unclear, and we'll try to address it during the talk. Hopefully, we won't have too much of that. So I'm going to give you an overview of high-performance computing as I see it today, and we're going to look at some of the things that we have to adjust to as we go to extreme computing. And I'm going to use the word petaflop and exaflop. Petaflop is 10 to the 15, exaflop is 10 to the 18 floating point operations. So I'll talk about floating point operations, and whenever I mention that word, I'm talking about 64-bit operands. And the operations I'm talking about are adds and multiplies. We usually don't have to worry too much about divisions, but those are the things that we'll be looking at. Okay, so first off, almost a year ago, in July of last year, this executive order from the White House came out talking about a national strategic computing initiative. So Obama signed this executive order, and this executive order did a few things. It had 5 strategic themes. It says it's going to create systems that can apply exaflop computing power to exabytes of data. Now, I didn't say exabytes and exaflops. Obama said that. Okay, so that's Obama's words. It's to keep the US at the forefront of HPC capability. It's to improve HPC application developers' productivity. It's to make HPC readily available and to establish the hardware technology for future HPC systems. So that's sort of an important thing. It sort of gave at the very highest levels of government recognition that high-performance computing is important. Having said that, there was no money associated with this. This was just an executive order. So it said this isn't important and we should focus on it. So funding, may or may not come. We have a dysfunctional Congress. Who knows what's going to happen? Fortunately, HPC is one where I think everybody would agree it's going to be important. So here's the state of the art of, let's call it supercomputing today. So petaflops, 10 to the 15 floating point operations per second. We have 81 computing systems which have that capability. 81 computing systems have achieved petaflops or more performance. And we'll talk about where they achieved it in just a moment. There are 3 technologies that we're looking at to go forward as we move to even higher rates of execution. And those technologies are built on a number of things. So one technology that we're thinking of for building that next generation of computing systems is built on commodity parts. That is, take a lot of Intel processors, put them together in a box with an interconnect network, and make that run as a parallel computer. Right? We do that today. The second technology, swim lane, is to take those commodity processors and augment them with an accelerator, something that boosts performance even higher than we get out of the commodity processor. We use that in a way to maybe offload computation to this accelerator to boost performance, and we get something which is much greater performance than we had with just the commodity part. So that's a second technology that's being deployed today for high performance computing, and we're looking at it for the future. And the third is to use special purpose lightweight processors, put them together somehow and interconnect that together in a large system and use that as an aggregate to solve our most challenging problems. And examples of that would be, today we have an existence example from IBM. IBM produced a Blue Gene computer that's deployed in a number of places, lightweight special purpose processors, specific in some sense for high performance computing with a very fast interconnect network. And we'll see a few of those are in place. ARM is another one, lightweight processors. Lightweight in terms of perhaps its functionality compared to a heavyweight processor like a traditional Xeon processor, and maybe lighter weight in terms of the power consumption. We'll see power is going to be a big deal, as you probably are aware. And another one is the Knight's Landing. So Intel's about to officially announce this chip, 32 cores, x86 architecture, self-hosted. So this is not an accelerator that you put next to a host. It's something which you run directly on. So you would log into that machine and make a run if you wished. Today we see interest in supercomputing, which is really worldwide, and there's many markets that are engaged in high performance computing. We have this list of the 500 fastest computers, and we'll take a look at that in a moment. But if you take a look at that list in detail, what you notice is that about half of the machines on this list are used in industry. Not in research places, not in an academic situation, but in industry. So industry gets it. These machines provide some kind of strategic advantage that lets them do their job more competitively than others. So they're investing in high performance computing to help augment whatever they're doing. And that's sort of an interesting track. Those machines tend to be at the lower end of the list, not at the higher end. Exascale projects, 10 to the 18 floating point operations per second, projects that are looking at exascale, exist in many countries. So we have an effort going on in the US, there's an effort going on in the European community, efforts in Japan, in China, and other places are engaged in looking at high performance computing. And something that's perhaps striking, on that list of the top 500 computers, Intel processors have the largest share. So of the 500 computers, 89% of those computers are based on Intel's processor, x86 architecture. And AMD has another 4%. So x86 is really driving this. 93% of the machines are based on that technology, which is a stunning number, I find. Okay, so we're going to look at these, we're going to look at the fastest computers, and we're going to do them through the eyes of this data. It's called the top 500, and it's based on running a benchmark on a computer. And we run a benchmark on a computer, and then we rank the computers based on the performance they achieve on that benchmark. So the benchmark, for better or worse, and at the end of the talk I'll describe some of the problems here, it's the Linpack Benchmark. So Linpack is a package of software, and during the time of the benchmark, during the time of that package being created, we came up with a test, AX equals B, solving a standard dense matrix problem. What we did is we looked at what was the performance for solving that problem. How many operations do you do? It does 2/3 n cubed operations. How much time does it take to solve that problem? AX equal B. I'm going to give you a matrix A. It's a square matrix. It's a general matrix. And I'm going to give you a right-hand side B, and I'm going to ask you to compute X. The ground rules for this benchmark and for the top 500 say you must use Gaussian elimination with partial pivoting. Right? So you have to use that algorithm. You can't use some iterative algorithm. You can't use the QR factorization. You can't guess the solution. You have to use that. You have to use that algorithm. And people have tried a number of things to get around that. And typically what we see as you increase the size of the problem, if you increase the size of the matrix A, the rate of execution goes up until you reach an asymptotic point. And we want to capture the asymptotic point for your machine. And basically you fill up your machine with a matrix and you solve that problem, the biggest one that you can. And that's how we get at this top 500 number. So this list of the 500 fastest computers is updated twice a year. It's updated in November at a meeting called SC. It's a meeting where we have about 10,000 of my closest friends attending. And it's also updated at a meeting in Germany called ISC. And that meeting's coming up next month in June in Frankfurt. There's about 2,000 people that attend that meeting. And if you're interested, there's a website that contains all the data that we've collected over the past 24 years. So this has been going on for a long time. Okay, so this is a snapshot of that 24-year period. So we're looking at times when the benchmark has been released twice a year, and we're looking at the performance achieved of that benchmark. This red line is the #1 machine, so that's the fastest computer over time. So the fastest computer today is this guy, so that's at 34 petaflops. That's what it achieved for running that benchmark. So it ran the benchmark, we looked at the time to solution, we checked to see if they got the right answer. There's a standard test you can do to verify they've in fact computed the correct solution to that problem. And they rank #1. We'll talk about that machine. It's been #1 for a while, for 3 years. I predict it's going to be dethroned at this year. And this is the guy at the bottom of the list. So that's the entry point, if you will. That's the guy that just made it on the list, 206 teraflops. So that guy just barely squeaked into the list. So that's sort of bracket supercomputing, if you will, over time. And that orange line is that's an artificial number. That's the Excel sheet computation. So we got 500 machines, you see the performance, add up the performance. And today it's at 420 petaflops. So not quite a half a exaflop in the aggregate performance of that. Again, that's an artificial thing. Nothing was run on all those machines simultaneously, but all the machines ran the benchmark to get that performance. And there's many stories about how long it took to run the benchmark. I think the record for how much time it took to run the benchmark is something like 28 hours. So you start it until it ended, solving the problem was 28 hours. The biggest matrix was on the order of 10 million. This is a big matrix solving. And so you see what's happened over time here. When we first started, the fastest machine was at 60 gigaflops, so 60 billion floating point operations per second. And the lowest machine was 400 megaflops. And things change very rapidly. Well, first off, a machine that's #1, it takes 6 to 8 years to fall off the list. So the #1 machine typically costs $200 million. That's for the hardware. So that's the investment that's made. And if you want to continue to be in the #1 position over time, you need to make that investment every roughly 6 to 8 years. Probably more often if you want to continue to be thriving at the top end of this list. And the guy at the bottom of the list today, this is the striking thing about these exponentials, that was equal to the sum of all the computers in 2001. So again, things change very rapidly here. And sometimes when they change so rapidly to the things I use on a daily basis, I have a hard time predicting where it's going to go into the future. So my laptop. So this is a machine which is an Intel-based machine. It has a dual core. It runs I can run the benchmark on it. I run the benchmark. I get 70 gigaflops out of my laptop. So that's a machine that I use to read email, right? That's a stunning thing that's happened here, right? And not too long ago, that would have been faster than the #1 machine. So the #1 machine in 1993, that was a Thinking Machine CM5, and it had 1,000 processors in it. It was at Los Alamos National Lab, solving the challenging problems that they have. And today I have something which I use on an airplane which has a battery which lasts about 12 hours. So that's an incredible change, in terms of just a short period of time that's taken place in we have here. $200 million. That's the price. The number one machine is $200 million. And roughly. Okay, a little bit less maybe, but roughly that amount of money in 1993 dollars. Okay. Okay, so things change rapidly. So my iPhone. So my phone, I can run the benchmark on it. There's an app for that. You can download the app and run it on your phone. Absolutely. 4 gigaflops. 4 gigaflops out of my iPhone. And I wear that on my belt, has a battery life of maybe a day. That's an incredible achievement. That would have been on the top 500 list in 1997. And you may not appreciate that number, but a Cray 2 was 4 gigaflops. A Cray 2. Cray 2 was this very exotic machine, would sit in the corner, was liquid cooled, used at Los Alamos and many other places that solved the most challenging problems of its time. And I've got something which I casually wear on my belt. It's sort of stunning achievements. Yeah.
What's the version of the iPhone?
What's the version? Yeah. I've got an old one. So even the iPad 2 Pro, or the iPad Pro, which has a very powerful ARM processor, we're just in the process of, unfortunately Apple changed their programming model, so you got to rewrite everything to get this new model. It's taking us a little bit longer, but we predict that'll be very, very, very impressive. I don't know what it's going to be, but I'm sure it's over 10 gigaflops. It'd probably be closer to 20, 30, 50 gigaflops for that thing. Okay, there's a funny inflection point there. So we like to make projections and predictions out of this thing. So we're not quite sure what's happening here. Some people say maybe that shows the end of Moore's law. Right? Moore's law can't go on forever, so maybe that has some impact here. I think it has more to do with the investment that's made in high-performance computing. It has something about this machine being on the number one for such a long period of time. And I think that maybe with the economic problems, 2008, it didn't. We didn't see such an investment continue. So maybe that's that. Maybe that's an inflection point. We'll have to wait and see how things go. So here's a list of the top 10 computers. So this is the top 10 list of computers. This is the number one machine. The way to read this is this machine is located at the National Supercomputing Center in Guangzhou. It's a machine that was built by a machine that has a name of the Tianhe 2, and it was built by the National University for Defense Technology. So they are the guys who are the integrators for this machine. So they did the integration. This machine is based on Intel's processors, a 12-core Xeon processor, together with Intel's accelerator, the Xeon Phi. That's the last generation of Xeon processors. And they have a custom interconnect. So, this is a large machine. They're passing messages around, and the interconnect that they use, they built themselves. So it's not InfiniBand. It's a proprietary thing that they constructed. NUDT has been in the business of building machines for many years. It's in Chengsha. So it's a Chinese machine. It has 3 million cores in it. So 3 million cores, right? So if you're programming this machine at scale, and these machines are designed to be used at scale, otherwise you'd buy a bunch of smaller machines. It's much more effective. So this machine, 3 million cores, and you have to have 4 threads of execution per core to effectively get a high rate of execution. So for the benchmark, they had 12 million threads of execution running on this system, right? Passing messages around between the nodes in the system. And they achieved 34 petaflops. Alan?
What's the mean time to failure?
That's a good question. What's the mean time to failure for these machines? This machine here, you do this benchmark when you're first installing the machine. The machine time to failure was measured probably in terms of hours. So they had parts that were failing. They had their own network that was flaky, I'm sure. Software is another source of problems with these machines. So they had a hard time keeping the machine up long enough to run the benchmark. So the benchmark doesn't have any fault tolerance stuff in it. You have to run the benchmark. And the benchmark, in this case, I don't remember how long it took. I think it was maybe on the order of 8 hours for this particular thing. So they had to keep the machine up and running for 8 hours. And they didn't do that in one run. They did that over a period of probably 3 weeks, 3-4 weeks to get this machine up. There's a various adjustments you have to make for tuning purposes. So it achieves 62% of the theoretical peak performance. So the theoretical peak is a paper and pencil calculation. How many cores do you have? What's the cycle time? How many operations do you do per cycle? And that gives you the theoretical peak performance. And then you run something on the machine, and they get 62%. So where did the rest go? Well, you have pass messages. So data movement's going to be an important thing. You got the program, and you got overhead with various things going on in this program. So they achieve 62%. The power needed to run this machine under load is 17 megawatts. So in the US, a megawatt year costs $1 million. So in my house, if I was to draw 1 megawatt over a period of 1 year, I'd get a bill from the electric company about a megawatt. That's in Tennessee. We probably have lower power costs from the TVA. I don't know what the costs are in China, but it's an expensive machine is the point to run. And that's the cost just for the memory, for the network, and for the interconnect. It doesn't include cooling. Cooling, you add another 30%. Okay, and then disks and lights in the room and stuff like that you have to include as well. So these machines are pretty expensive. This is a measure of efficiency. How many flops per watt? So today we're about 2 gigaflops per watt is that number, 2 gigaflops per watt. And then there's the other machines that we see on the list. This is the machine we have at Oak Ridge. So this is a machine made by Cray. It's called Titan. It uses AMD processors and an NVIDIA GPU as an accelerator to boost performance again. Right? And it's a custom interconnect made by Cray. So Cray's secret sauce, if you will, is their interconnect. They don't make processors. They don't make memory. They make the interconnect, which they just sold to Intel, by the way. Or not just, they sold it a while ago. And our machine has 500,000 cores in it, so much less core count. It's about half the performance, 65% of theoretical peak, about half the power consumption of that machine. Yeah?
Which of these two is getting more science or engineering on it?
So how do you judge that is the question. That's an important question, of course. Why do you build these machines? Well, to solve challenging problems, to push back the frontiers of science, to do things that you couldn't do on a smaller machine. So they make an investment to hopefully do that. It's hard to get a gauge of that. So how many papers, how many covers of science do you do? There's many ways you can measure that. I know about Oak Ridge, and I know I can give you a track record of many of the accomplishments that have been achieved through that. I have a harder time with the Chinese machine. But they have published papers on it and so on. Another measure is how many Gordon Bell Prizes have you won? That's another thing that people might measure. So yeah, many things going on here. You could see the top 10 machines. Many countries. China has one. The US has a bunch of machines. DOE, Department of Energy, is a big investor in high performance computing. So Department of Energy, that's a big deal. Computational science is the thing that's driving science today in the US. And the Department of Energy is investing heavily into this area. Department of Energy has two parts, right? It has what's called the Office of Science, that's Oak Ridge National Lab, OS, Office of Science, and it has the Defense Program, NNSA. One is classified and one is not. Open Science is the unclassified stuff. NNSA, they do weapons research. Yeah.
Is there a reason that the Japanese supercomputer is just way more power efficient than all the other ones?
It was designed to do supercomputing. So the Japanese built a processor and an interconnect specifically for this purpose. So that was what their mindset was, build a supercomputer. Remember, these guys are taking Intel parts, the stuff that's in your laptop, or not laptop, but in your desk side machine. And they're slapping together many of them, together with an accelerator. And that wasn't designed to do supercomputing, as we'll see. So, there's a reason why this machine is so much more efficient. So in fact, when I first saw that number, I thought it was wrong. I thought they cheated. 93%, they can't do that. And then, you look around and see that and say, sure, that's it, yeah.
Yeah, the peak usage is really good, but you look at the megaflops per watt, it's really low.
So megaflops per watt is another thing to look at in that context, and that is a lower number than the other machines. That's right. So maybe it isn't the most efficient in that context for running this thing. So there's many things to look at and many reasons for these things overall.
Is the green contest still going on, the green 500?
Yeah, the green so there's another. So we have the top 500, and there's the green 500. There's the graph 500. There's many 500s. So the green 500 measures power efficiency. So we're going to announce, big secret, that the green and the top 500 guys are going to get together and produce one list, which will have all the information in it. So that'll be a useful thing, maybe. Okay, many countries, the US has Japan, as I mentioned, Swiss have a big supercomputing. The guys in Stuttgart, Saudi Arabia has a big supercomputer. So colleague at KAUST is, yes.
Side question.
Sure.
If you compare this with the computational capacity and the needs in data centers,
The data centers, yeah.
how much is this? Is this stuff dwarfed by the amount of computation that goes on in data centers?
Right, so I went to Google and says, hey, we got this benchmark. We want to run a benchmark on your data center here. Would you please, run this benchmark? Shut down Google, run this benchmark for 28 hours, and send us a result. They sort of laughed at that, of course. Yeah, so they have very powerful systems. They're using much cheaper processors than what we see in these devices here. They don't have the need for that high performance floating point capability. Failures, when they occur in Google, I try again, right? So it's not as critical, let's say, as some of these machines here. So there's many things which are different, but they have very powerful data centers. The megawatts are even higher than what we see here, almost double what we see here. So that's a lot big things going on, and that's true of all the big data centers. Okay, so what do we see? Large core counts. These are big machines. You got 3 million, 1.5 million cores, and so on and so forth down the list here. We see power consumption, large power consumptions with these machines. We see accelerators being used. So I mentioned three potentials for the future architectures, and they emerge here, of course. So this is a machine here which just uses Intel parts, just commodity processors inside this machine with a custom interconnect. We see accelerators being used, and then we see Blue Gene, which is this specialized processor lightweight core in the machine at Livermore and also at Argonne National Laboratory. IBM has decided they're not going to do this anymore, and they're dropping the Blue Gene series, so that's a historic artifact now. Okay, so I just want to mention something about accelerators here, because this is sort of the crux of a problem that we're going to see over and over again. So we're going to use an accelerator, something like a GPU. And the way this works is we've got a host processor and an accelerator. And the host processor is in charge. What you have to do is move data to the accelerator and then tell the accelerator to do something. And then asynchronously, you go off and do something else. And later you come back to see if it's finished doing that operation, and then you get it back. Today, the accelerators are connected through something called the PCI Express, and that's a DMA connection which connects memories together. So the way this works is this guy's in control. He will take information here, pass it over this link, put stuff into its device memory on the accelerator side, and then tell this guy what to do some operation on it. But notice here that this guy here is pretty powerful. This is a teraflop sitting here in this GPU compared to the host processor. Much less, order of magnitude less performance coming out of it. And we're going to be passing information over this link here, and notice this link connection. It's 1 gigaword per second. So we got stress points here in this machine. There's a stress point here in this architecture at 64 gigabytes per second, moving data from the host, from the memory of the system, the primary memory, up to cache. That's sort of the speed at which data moves in the host processor. In the accelerator, we have 288 gigabytes is the data rate that data can move around this system. And over here, we've got something which is running at 8 gigabytes. So very high performance potential, but very poor movement of data between those two. So data movement is going to be the strangle point. So you're going to pass data over, and you better have a lot of operations to do on the data. Otherwise, you're going to be killed by that data rate, moving data back and forth across that link. That's going to kill performance. So today, that's an issue with accelerators. The future, that'll be changed. That's all going to be modified and affected in the next few generations. But that today is one thing we have to live with. So we got 1 gigaword per second and 1 teraflop worth of performance capability. So you better move a lot of data over there. Okay, top 500 machines. This is a graph which has 500 rectangles. These rectangles here represent each rectangle represents a computer. The area of the rectangle represents the performance that it achieved. So the largest rectangle is this guy here, right? So China, the US has 201 computers on the top 500 list, the recent list. China has 109 computers. In 2001, China had 0 supercomputers. So this is an incredible investment that China's made in terms of high performance computing, right? They realize this is sort of an important thing going on. Japan has 38, UK, France have about the same, Germany has 32 machines. You know, the striking thing here, China tripled the number of systems in the latest list. 3 times, they went from something to 3 times, and that number is 109. So it went from roughly 33 machines to 109 systems on the list. You know, it's a tremendous impact. US is now fallen to the lowest point since we've been keeping this information with 201 systems. So that's sort of an interesting artifact. The Department of Energy has sort of announced that it's going to put in place 3 large systems, and those systems will be put in place at the end of 2017 and be in production in 2018. So these systems are cost roughly $200 million each, a little bit less. Oak Ridge and Lawrence Livermore National Lab. Again, this is an Office of Science lab, and this is an NNSA lab, a defense-related lab. They're going to get an IBM machine with NVIDIA parts, NVIDIA accelerator, and a Mellanox interconnect. So that's their form of the machine, IBM's newer processor, Power 9 architecture. And Argonne is going to get a machine based on Intel and Cray. It's a collaboration. Cray is going to participate in some of the integration that goes on. And these machines are going to be over 100 petaflops in terms of the performance, over 100 petaflops, an order of magnitude greater than what we have now. And then after that, the next generation of machines for the Department of Energy gets to an exaflop. So that's the plan. 2018 deployment of a machine of about 100 petaflops, and then the exaflop. They're going to hit exaflop around 2023. That's the current thinking when they get to exaflop computing. The US Department of Commerce last year in February said they're concerned about how the Chinese are using US technology, and they're going to embargo the use of that technology in 4 places in China. So they said these guys are on a blockade list. You can no longer receive Intel parts to build machines. So the boycott exists at the Supercomputing Center in Guangzhou. That's the guys that have the fastest computer. At the National Supercomputing Center in Tianjin, that's the guy that has a very powerful system built on top of Intel parts. The National University for Technology, they're the integrators, they're the developers of these machines. They're boycotted from having parts. And the National Supercomputing Center in Chenchaa, that's where the NUDT is located. So that was an interesting statement that the US Department of Commerce about boycotting that. And the results of that, maybe it's predictable. Chinese they're going to expand their hardware and software efforts, and they're going to make it so that it's anything but US. So they announced 3 machines that they're putting in place, very large systems, 2 of them over 100 petaflops. So that's based on the Shenwei processor. So that's their own processor. It's a multi-core processor that they're going to build out a machine. That machine's going to be announced in June. So next month, that machine will be announced at the National Supercomputing Conference in Frankfurt. NUDT is on a path to deliver an upgrade for this machine. That's going to be based on a 100 petaflop system that uses ARM processors. Right? So China, again, is developing their own architecture based on an open architecture of ARM. And the Chinese Academy of Sciences has a project to do their own processor, called the Godson processor, that will be based on a MIPS architecture. Right? This architecture, the Shenwei, is based on alpha instruction set. And the latest 5-year plan from China says that the government is pushing to build out its domestic high-performance computing efforts, and exascale systems will be developed that will not use any US chips. So they've received a tremendous inflow of research funding in China to build out their high-performance computing with an eye towards pushing out the technology. And so they get it. They got the message loud and clear, and they're investing in the way to develop their own systems. Yeah.
How many cabinets will the Shenwei be?
I'm not sure. I haven't seen the details of the machine has not been announced. I have some vague information about the system. I think it's a chip which has 206 cores, They've got one heavyweight core and then 4 things which have lightweight cores in it. MIMD, Nature, and those 4 things doing lightweight cores. I'm not really sure about the architecture. It's vague. It'll be announced next month, and I'm sure we'll get the full story.
That's a reverse engineered alpha?
No. The instruction set is alpha. There's no reverse engineering. No. So what instruction set should they use? Well, x86 is Intel's and AMD's, although AMD just signed something with China, so there's a back door for China to get into the x86 market. Everything's about software in the end. You got to build software. If you have x86 based, there's a tremendous volume of software that you can use. If you're going to start something new or use something which is in the open, you may have to develop software, and that's a big expense that you have to incur. Building something on ARM, I've talked to the software engineers in China that are building this, and they just shake their head because they've got to build the whole software stack up for this high performance machine, and I can imagine that's a formidable challenge to take on. Okay, so you know the story as well as I do. Gordon Moore made this projection a number of years ago. Something's going to double every 18 or 24 months, depending how you read the story. And we've had this incredible ride based on that conjecture. Intel parts follow that curve in a very natural way. We've got things which have incredible number of gates on the chip following that rule. So that's a really a great story. Smaller, faster, more powerful things have evolved from that. But the real secret sauce here is not Moore's law, it's Dennard scaling. So Robert Dennard was a researcher at IBM, and he realized this incredible situation that's in place today. So he observed that the voltage and current should be proportional to the linear dimension of the transistor, and that translates into something that basically says, this feature size, if we decrease it by a factor, then we can decrease the voltage by that factor, and we can have the number of transistors increase by the square of that, the area of that, and the clock speed can be increased by that factor. So the energy consumption under these conditions doesn't change. That's like an incredible situation, right? So you get twice the number of transistors, 40% faster, and 50% more efficient. So it's because of this in the old days, when I got a new processor, a new desk machine, and I ran my application on the new machine, it ran faster. I didn't have to do anything. It just ran faster. I was the delighted guy. I didn't have to invest in anything except buying the new machine and running my application. So Dennard scaling gave me that ability. Unfortunately, Dennard scaling breaks down, and the breakdown occurs because of the feature size getting too small, current leakage occurs, and the chip starts to heat up. So what we see is for our chips, this is a plot here of cycle time for chips over time. We see the cycle time rising over time until it reaches this point here, and then we get this flattening that occurs in the cycle time of new chips that occur, right? And that's around 3 gigahertz. So 3 gigahertz is roughly where the cycle time is frozen, and that's because of Dennard scaling, the breakdown that occurred in Dennard scaling. So this was caused by Dennard scaling. Moore's law gave us the gates, but Dennard scaling gave us that path in a way to use that in a very productive way. So the breakdown of Dennard scaling in roughly 2004 led to multi-core, right? We got all these gates that we have on our chip. What are we going to do with them? Well, let's make more processors on the chip. So cores now evolve on the chip, and now that hardware issue became a software problem. Because when I get a new processor, I have to do something. As a software guy, I have to invest in parallel programming in order to get the advantage of the new processors that are coming out. So I have to make changes to invest in. In the old days, remember, I just put my application on the new hardware, and it ran faster because of Dennard scaling. But now, because of the multi-core, we have a different scenario evolving. Okay, so here's the story that Intel has played out on us over the past few years. So Intel Xeon processors, they've been around for a while. And when they first came out, the Xeon processor, each core now, I'm talking about a core of a Xeon processor, each core was capable of 2 floating point operations per cycle. They would complete 2 floating point operations every cycle. When Nehalem came out in 2009 and Westmere after that, they doubled that. So each core produced 8 floating point operations per cycle. That's 64-bit arithmetic. Single precision is always double it. I always get double the performance. Sandy Bridge in 2011 doubled it again. 8 floating point operations per core per cycle for that machine. So floating point operations here are really quite available on these processors. Haswell, which my laptop has, does 16 floating point operations per cycle, right? And the Xeon Phi also is at that same rate of 16 floating point operations per cycle. The new processors that are coming out from Intel and the new Knights Landing processor will do 32 floating point operations per core. That has 72 cores in it. So you can do the count in terms of what their performance might be. That's an incredible amount of floating point capability in this processor. Incredible. And can we effectively use that? That's the real question. Can we effectively use it in our computations? Here's the problem. Memory, data has to come from somewhere to be used in that processor. Data comes from memory across a bus, and the buses that we have today, it takes 167 cycles to move the data from memory to the point in the processor where it's going to be used. So in the time it takes to move the data, I could have done 2,600 floating point operations. So data movement is going to be sort of the strangle point, if you will, for anywhere getting near the kind of floating point operations. So I want to go through a couple of examples here. This is my laptop. This is based on an i7 Intel Core i7 processor. It has a Haswell processor. 2.3 gigahertz is the nominal cycle time. It has something called turbo boost. So this is something that's architected in the machine. And if the machine can increase the cycle time and not have a stress in terms of the heat generated, it'll raise the cycle time. So the cycle time can be raised to 3.5. So that's something that happens without my doing anything. The turbo boost kicks in because it detects that we're not going to melt the chip, and it raises the cycle time to 3.5 gigahertz. So that translates into 16 floating point operations per cycle at 3.5 gigahertz. 56 gigaflops is the theoretical peak performance for one of the cores in my laptop. That's an incredible number. That's an incredible number. So here's the design. I have a CPU, I have cache, 6 megabytes of cache, I have memory, 8 gigabytes of memory, and I have a path from memory into the cache. And that path says 25.6 gigabytes per second. That's all architected into the machine. I can't do anything about that. And I want to see what happens if I run a model. So I want to do some operations now on my laptop. And I want to do this operation. These are level 1 BLAS operations, basic linear algebra subprograms. The BLAS operations here are DAXB. Take a scalar multiple of one vector and add it to another vector. So that's a vector operation. Data's coming from memory. We're going to do that operation, and it takes 2 vectors in, and it shoves one vector. It's actually 3 vectors in, does some operations, combinations, and shoves one vector back, the results. Or a dot product. Take 2 vectors in, multiply them together component-wise, and sum them up, right? So those are the 2 operations. Each of those, we do n multiplies and n additions. And that's the basic structure. And again, we have some vectors to deal with. So let's see what happens in my model. And I'm going to make these vectors very large because I want to reduce latency. I want to remove latency from the issue and just look at the bandwidth concerns. So I'm going to fill up cache. So in order to fill up cache, n, the vector length, is 375,000. So that's the vector length that we have. I'm going to read that into cache and then do the floating point operations. So the data movement, I'm going to move this amount of data. I'm going to do 8 bytes of that, and that's 3 megabytes. I've got 2 vectors that I have to deal with. I'm going to do an inner product. So 2 vectors fill up cache perfectly. And then I'm going to do the floating point operations on it. Do that multiply and add to get that single results. So the time to move the data from memory to cache, I can measure that. It's 6 megabytes. The bandwidth is 25 gigabytes per second. So it takes 0.23 milliseconds to move the data. So that's the data transfer rate. To do the floating point operations, I've got 2n floating point operations at 56 gigaflops. That says it's going to take 0.01 milliseconds to do the floating point operations. So if I look at that and I assume that I can overlap the data movement and the vector operations, that says that this thing here is going to take 0.23 milliseconds, and that's 3.2 gigaflops is the effective execution rate for those vector operations. So remember, the peak performance here is at 56, right? So I'm not coming anywhere near the peak performance of this processor. So this operation is communication bound. I get no reuse of data. I read in two vectors, do something, the vectors are thrown away, and I don't reuse the data. I can only get performance perhaps if I reuse it. Level 2 BLAs do matrix vector, and level 3 BLAs do matrix matrix. So let's see what happens with a matrix times a vector. Again, I'm going to make things large enough to fill up cache. I'm going to move a matrix in. The matrix is of size 860. And that will perfectly fill up cache along with the vectors associated with that matrix times vector. These are dense matrix vector operations. So again, the time to move the data, I've got 6 megabytes of data, is 0.23 milliseconds. The time to do the floating point now, I've got 2 n-squared floating point operations to perform at 56 gigaflops. That takes 0.26 milliseconds. So now the floating point is taking more time than the data movement. And let's say I can overlap them. If I overlap them, that says that for this operation, at this data movement with the floating point operation count, it gives me 5.6 gigaflops. So an order of magnitude off of the peak performance for a matrix times vector operation. So if I do that operation, that's the best that I can possibly achieve. Again, we have a situation which is memory bound. Okay, let's go one step further. Let's take 3 matrices. I'm going to make them of the size to fit into cache, 500 by 500 matrices in this case. That perfectly fills up cache with the 3 matrices involved. Again, I'm moving 6 megabytes of data from memory into the cache. Doing the floating point operations in that situation, I have in this case 2 n-cubed floating point operations. Matrix multiplies order n cubed. So I have a situation where it's order n squared data and order n cubed floating point operations. So now the time to do the floating point operations is 4.46 milliseconds. Much more time is spent doing floating point than moving data. So that's a good situation. And in this case, the model says we should run at 53 gigaflops. Close, very close to the theoretical peak performance for the processor. So this problem is not memory bound. So that was a model. How does it actually run? When I actually do the experiment on my laptop, what do I see? So here's the graph that I see. So this is the graph for the matrix vector. These are the vector operations, the dot product. So we see performance about 1.6 gigaflops. So if I do any kind of vector operations here, I'm going to be driven to the point of 1.6 gigaflops. I can't do any better. There's no reuse of data with vector operations. If I do a matrix times vector, I get 3.4 gigaflops. And matrix multiply, I achieve 54 gigaflops. Very close to the theoretical peak performance. These are actual numbers that have been achieved for, as you see, very large problems. So, you know, data movement's going to be a critical thing in applications to get close to the theoretical peak performance. The Linpack benchmark, the top 500 numbers, do matrix multiply. That algorithm can be expressed in terms of matrix multiply for the most part, and that's what's driving the performance for that algorithm. So we've had a long sequence of software that's been involved. I've been involved in the design of software since the late 70s. In that time, we had a package called Linpack. Linpack Benchmark is derived from that package. And the package was designed around vector operations. It was designed to use Fortran to operate on vectors by column. We had vector machines. We thought column operations would be a good thing to do on that machine. And that's the way the algorithm was structured. So the factorization routine, LU factorization, you update a column of the matrix, may introduce zeros down the column, and then apply a sequence of transformations which basically updated this block of data, updated a tremendous amount of data. So we get a lot of data movement in this algorithm based on vector operations. And we learned from that experience that that wasn't a very good thing. As the architectures evolved from vector to machines based on cache design, where we had a cache that we can effectively get reuse of data. So we designed our algorithms in the next generation, LAPACK, to look at blocked algorithms. Instead of taking a column, we would work on the side to develop a sequence of transformations that would introduce zeros in a panel of the matrix, in a trapezoid of the matrix, and then we would update the matrix, the trailing part of the matrix, by doing a matrix multiply. So we could effectively get very high performance out of that part of the computation. and that worked very well for a number of years. And there's sort of an evolution of software that happened based on that. Vector operations, cache-based systems, distributed memory use that same basic model, except doing message passing within it, and that was a package called Scalapack. Today we're redesigning all of that software. All of that software does not run at top efficiency on today's machines. And one of the other things that we have to keep in mind that the classical analysis that we do for these algorithms may not be valid today. And the classical analysis says you take a look at the number of floating point operations, you take a look at the time, and the algorithm that did the smallest number of floating point operations was generally the best algorithm to use. That's sort of common wisdom, if you will. So today that common wisdom doesn't effectively hold. And here's an example. This is looking at 3 generations of computing the singular values of a matrix. So there's 3 generations. There's a package called IcePack, which had a routine to compute the singular values of a matrix. It was designed originally around an ALGOL code. So the ALGOL was translated into Fortran. The Fortran was implemented in a very naive way, and we got performance which today runs very poor. Linpack was column-wise organized, as I mentioned, and LAPack tried to effectively use the cache. So this is looking at, and this algorithm here is an algorithm which takes a matrix. In this case, it's a square matrix. It could be a rectangular matrix. It goes through 2 stages. It reduces the matrix to a bidiagonal form through a direct process of introducing zeros into the matrix in a very structured way. And then after we get this bidiagonal form, there's an iterative process that takes over, which introduces small elements and effectively through an iteration drives down the off-diagonal elements of that matrix. So that's the standard way in which we compute the singular values of a matrix. So this experiment looks at a Sandy Bridge processor. It's a dual socket 8-core processor. The IcePack algorithm only uses 1 core. That's all it can effectively use. That was just the straight Fortran code, and its performance is the thing we normalize all the other implementations. They're all doing the same thing. They're all getting the same accuracy. This light blue line here represents the Linpack code implementing that algorithm in a very straightforward way. The comparison shows an improvement over that naive Fortran translated from ALGOL. And the Linpack code does things in a blocked-oriented fashion, and we see a significant enhancement. All of those use 1 core. When we engage in multi-core, using this guy here has 16 cores, dual socket 8-core processor, we end up with a performance enhancement which looks something like this over the IcePack. So that's roughly 40 times faster than that IcePack version. Same number of floating point operations in this case. Being exposed, but we get something which is 40 times faster than the very naive implementation that we have with the IcePack code. If we take a look at what's going on in the LAPack code, we're going to reduce the bidiagonal form. We go through a process. There's sort of 2 basic operations that we have to do. One is a matrix vector operation, and another is a matrix multiply. Remember I said matrix vector runs at very poor performance, matrix multiply runs at very high performance. Half of the floating point operations are using matrix vector. So we're going to be driven to a very, very low point in terms of the floating point potential for this thing, and it's memory bound. So the basic structure of doing a singular value decomposition is going to be memory bound. So the idea is to see if we can reduce or get rid of some of these things here by changing the algorithm. So because we don't want to end up with an algorithm which is going to be driven to this matrix vector kind of performance. So the structure that we have today is a 2-stage algorithm. It reduces a matrix to a banded upper form, and that's done with a process which does matrix multiply exclusively. So that's something that's going to be driven to the highest levels of performance. And then we take this form of the matrix and we sort of gnaw away at the upper diagonals of this matrix here, introducing zeros in a way which is very cache friendly. So we're going to get reuse of data. That algorithm is not matrix multiply, however. It's something which we call BLAS 1.5. So it's a combination of level 1 BLAS and level 2 BLAS operations. But it's done in a cache-friendly way. So what we end up with is an algorithm which takes many more floating point operations. So the operation count for this algorithm, which is this 2-stage thing, is n n over 3 n cubed floating point operations plus something else. The original algorithm did 8/3 n cubed floating point operations. So this algorithm, which is basically structured to do matrix multiply as the kernel, does 25% more floating point operations. So a tremendous more large number of floating point operations, but the performance is stellar in terms of what we see because matrix multiply is driving that computation. We're getting the benefit of that potential that we see in the processor. So we have an algorithm here which is basically 6 times faster than the old algorithm in terms of the time to solution, even though it's doing 25% more floating point operations. So that conventional wisdom of the number of operations translating into time to solution is something that we have to moderate a little bit in terms of our overall structure. Okay, we're making enhancements to the way in which we do parallel processing as well. Many of the algorithms we have do loop level parallel processing. There's a loop, we run iterations of the loop in parallel, and we can exploit many, many processors in that process. If you do that, however, the loop terminates, and then we all have to collapse down to one processor. There's a fork join thing which is going on there. There's a bulk synchronous processing that has to occur. And that's going to kill you. I mean, think about programming for 12 million threads of execution, and now you have to come down to one thread. So you've got all these things running, and then you're going to collapse down to this one thing and wait until that everybody else acquiesces until you move on to the next stage. So that's really going to destroy the performance that's there. So if you take a look at it in terms of a cartoon, this LU decomposition, fork join parallelism followed by a sequentialized step as you iterate through that process. On a 12-core or 16-core system, we end up with a performance diagram which looks something like this, where we have time evolving and cores being looked at. Productive cores are highlighted by color, and non-productive you see white space. So you get a thing where you engage a lot of processors and then you have a lot of white space, a lot of processors and white space associated with it. So what we're thinking of implementing, or what we have implemented, is a form of the algorithm which we try to overlap as much as possible. So as soon as we can start the second iteration, we do that, even before the first one is completed. So we get a head start, if you will. And since we're computer guys, we're not going to stop at one. We're going to do that over and over again. So we end up with an algorithm which tries to do as many steps as possible simultaneously. And if you take a look at that algorithm, it turns out to be one which is structured in terms of a data flow approach. One which has basically building a directed acyclic graph of the computation and then executing that directed acyclic graph on the underlying parallel machine. And when you do that, you end up releasing a large amount of potential parallel processing and avoiding that bottleneck around that loop level parallelism. So today, the packages we're designing replace the old packages with this model. So it's a model which today uses OpenMP to do the tasking. OpenMP has a very nice way of doing the task management. And we effectively generate a directed acyclic graph of the algorithm, and that algorithm, that DAG is executed by the underlying task model that's present in OpenMP. The structure of the code is based similar to what the old structure is. We're calling BLAS routines and using OpenMP pragma to define what the inputs and outputs to the tasks are, and then the runtime system in OpenMP manages that in a way which effectively does the execution. And in the end, we can take that computation which had a lot of white space and compress out that white space, looking at a DAG which has much less in terms of the overall execution. So I want to just spend the last few minutes looking at some of my sins, let's call them, of the past. I have to say that I became an accidental benchmarker back in the late 70s. So this is a project that I was fortunate to work on. These are the authors of that package. This is Cleve Moeller. Cleve's the guy who gave us MATLAB. This is Pete Stewart, who's a famous numerical analyst, and Jim Bunch, another famous numerical analyst. And this is a version of me when I had more hair. And this is my car when I was a student in New Mexico. And we designed this package and built it. And in the appendix of that user's guide, I have a table which lists the performance for a number of machines of the time running LU factorization with partial pivoting, solving a system of linear equations. So that's the origin of the Linpack benchmark. And I maintained that list and enhanced it over the past 40 years or so. To today, we have this thing called the Top 500. So Hans Moyer was the guy who came up with the idea of the Top 500. He had a list of the fastest computers looking at the peak performance. He knew I had a benchmark which looked at the performance actually on a problem. And he said, let's get together and produce this thing called the Top 500. So this is the first list of the Top 500. It lists the number one machine as being this CM5 at Los Alamos with 1,000 processors running at 60 gigaflops. So that's where that first point on that graph comes from, and then a number of other machines, 500 other machines were listed after that. The Thinking Machines was the number one in the first 4 machines, which is sort of interesting. Okay, so this benchmark has a number of bad things. Back in 1979, a floating point was expensive. That's where you spent much of your time, is in floating point operations, and the benchmark reflected what we saw in many of the applications that were running on the high performance machines of that time. Today, that's not the case. Our machines are over provisioned for floating point. It's not an expensive thing. Data movement's the expensive thing. So this architecture, or this benchmark, doesn't do a very good job of exposing flaws in the architecture. It does something which exposes the floating point operation count of the machine. It doesn't correlate with real applications. It encourages poor choices for architectural features, right? People want to be number one on this list, but they make choices in the architecture which are hard to really use from an application standpoint. So we're doing a disservice, let's call it, to the community. So we want to change that. So this is a new benchmark we're looking at, HPCG. It uses not a dense matrix, but a sparse matrix. It uses a matrix which is going to be solved using an iterative technique, conjugate gradient method. There's a preconditioner that's involved. There's a bunch of other things that happen during this iteration to stress parts of the machine. We're going to look at the dense and sparse parts of the computation. Collective operations will be done. We're using a multi-grid to help with the preconditioning step. So there's a number of things which have to be dealt with in that multi-grid step. And we're able to verify the solution and do all the other things that we feel we need to do with that. So this benchmark perhaps reflects better what happens on some of the big machines, at least some of the big machines at the Department of Energy. So it tracks better with the application potential, let's call it, on the machines, and it drives the, we hope that it will drive better choices in the architecture that's used if this thing here becomes a popular thing to look at. Okay, so there's a 3D problem, there's a 7-point stencil, there's, a 27-point stencil that's used in this particular problem, a bunch of conditions associated with it. So what we want to do is to compare the Linpack benchmark, HPL as it's called, with this new benchmark called HPCG and see how they match, how they compare. What kind of performance do we actually see out of these machines? I like to look at this as a way to bookend your computing system. One's going to show high performance and another's going to show poor performance. And applications are somewhere in between and probably more towards the iterative solution, towards HPCG. Okay, so here's a graph which is showing you the peak performance, that's the red dot, and the Linpack number. So that's doing a dense matrix problem. And we see that it's very close to the theoretical peak performance for these systems. And we're looking at systems, ranking the systems here and looking at the performance in terms of petaflops that we actually achieve when we compare these machines. And this is what we see from HPCG. So the HPCG performance is much lower than what we see from Linpack and far off of that theoretical peak that we have for those machines. Again, that's the bookending, if you will, for those machines. And this is sort of a table that we're putting together which shows the ranking. So this is the number one system. It's the same number one system on the Linpack benchmark. Yes? Here's a question.
Who was the one? There was like a standout. Who's that one?
This guy here? Yeah, he screwed up. So you always got somebody who doesn't know what they're doing, and this is clearly a case where he didn't know what he was doing. Okay, so here's the ranking. This is the number one machine on this list, and this is the Linpack achieved number. This is the HPCG achieved number. This is the percent of peak performance. So 1.1% of the theoretical peak performance, not 75, not 63, 1% of the theoretical peak performance we see on this. And this is a good implementation, I'll call it. This is not a bad implementation. This is somebody who worked at it and is doing as best as possible. And you see that trend in many of these machines. Here's that machine from Japan. They got a 93% peak. They're getting 4% on this one here. Even though the architecture is done very well, they're not capable of delivering more than 4%. So we see numbers between 1 and 4% on this top 10 list here. This is the second part of that 10 list, and I only show this to show this machine here. So this is a machine that's getting 11% of the theoretical peak, 11% on a problem which is really data communication bottlenecked. So what is that machine? So that machine is an NEC machine in Japan, and it's a vector machine. So this machine has a very balanced architecture between the floating point and the data movement. It's a traditional vector machine, so they're doing vector instructions on this machine, explicit large vector instructions, and they do a very good job of that implementation. So that's sort of the story. From the computing benchmarking side. Let me just end, if I can, with some things which I think are critical for high performance computing and the things that keep me excited, let's call it, or give me headaches. So synchronization reducing. We need algorithms which reduce the amount of synchronization we have in them. Fork join parallelism is not going to work when we have this level of parallelism within our machines at the top of this the top here. We need to get algorithms which reduce the communication. Jim Demmel, my colleague at Berkeley, has sort of cornered the market in terms of communication reducing algorithms. He's able to show this algorithm has provably the lower bound on communication, and then you implement that algorithm and you get something which you have a good feeling about in terms of its ability to deliver the right stuff. Mixed precision is another thing that really hasn't been exploited. Single precision and double precision. Single precision is twice as fast. So if we can exploit that, maybe start the iteration in single precision and later do something to refine the solution using double precision, that would enhance the performance. There's some very nice techniques that can be done, or let me call them tricks, that can be done even for dense matrices, where we're looking at iterative refinement, factoring the matrix in single precision, and then using this double precision selectively to enhance the performance. Auto-tuning is going to be critical. These machines are terribly complex and dynamically changing. We have to build into the software the ability to adjust to that changing environment. I can't leave it to the user to adjust all the knobs and whistles on the software. I have to build it into my software architecture. Fault resilience is going to be an important thing as we go to a higher number of processors. Coming up with algorithms that can can continue the execution in the presence of failure. You lose a process, you want to be able to continue the computation. You don't want it to fall over. Our model today with MPI is broken. There is no fault recovery except checkpoint restart. The other thing we're interested here is what about bit flips? So let's say a bit flips, can we detect that and can we correct that in the software, right? So we know we have ECC in memory. Can we do something along these lines? And you can do a number of things based on some algorithm-based fault-tolerant techniques to enhance that. I'll just mention bit flipping. So ECC memory, that's a great thing. We use it all the time. I'm terrified when people say they want to turn it off. In the GPU, it's easy to turn it off. So here's an interesting story. At Oak Ridge, we have a large machine, has a lot of memory. They looked at how many ECC single bit errors they had. They had 350, this is the average, 350 single bit errors per minute on this machine. Those are corrected because the hardware's there to correct it, but they're getting 350 per minute. I was stunned at that number. They get about 2 double bit errors per day on the machine, which kills the application. The application has to be restarted, and you carry on from that point. So don't turn off ECC. It's an important thing. There's an interesting article in IEEE Spectrum that Al Geist wrote. I think it was this month that talks about that. Reproducibility. Okay, so here's the thing. Today I can't guarantee the results are reproducible. That is, if I run the same application on a machine with the same data today and tomorrow, I can't guarantee you're going to get exactly the same results. And I can't guarantee that because I can't predict how collective operations are going to take place in the machine. I'm going to add up a bunch of numbers, and today they'll be added up this way, tomorrow they'll be added up that way. That's because of the hardware and how things are going to happen inside the hardware. I can't predict it. That's the way it's designed with MPI, in fact. So I may get round-off error differences. Now, that doesn't bother me. I can have a prediction on the error from the solution, and I can tell you what that solution should be up to that point. So the fact that I don't get the same error, I don't get the same results, perhaps doesn't bother me. Some people insist on getting the same results today and tomorrow. And to be honest, if I'm debugging a program, I want to get the same results today and tomorrow. Otherwise, I won't know where the error is occurring in my program. Some people who certify reactors have to get the same results as well. So that's something else we're worrying about and looking at, trying to achieve that by maybe turning a switch which does things in a very predicted way and is capable of doing things. Okay, so I want to just thank you for your time and attention. I've gone over just a little bit. I hope that hasn't been too much of a problem. We have major challenges ahead. Hybrid systems are here. Fault tolerance and power is a big deal, and we need many new ideas and approaches. It's an exciting time to be involved in high-performance computing. I think there's many interesting research problems that lie ahead for us to solve. So thanks again.
Maybe you can take a few questions.
Thanks for the fantastic talk. I just wonder how poor this, memory-bound algorithm can be. Suppose I have a memory-bound algorithm which I can parallelize. If I have like 2 or 4 cores on a chip sharing the L1 cache, should I not consider parallelize it? Because parallelize it, they basically make like 2 children, 2 cores, and they're starving, right? Other than 1.
Right, so I can't give you an answer yes or no, or you have to look at the application, you have to look at the, what the contention is, you have to look at what's happening in cache and monitor things in order to get a feel for what that might be and how you could circumvent that somehow. So there's no real yes or no black and white solution for that. You just need to look at things and see how it's affected. There are tools that we have that can probe that, look at cache misses, look at various things that can help with loads and stores and so on and so forth that can help monitor what's going on, but there's nothing there that's a clear solution, clear answer.
Do you have a prediction of when quantum computers will be available for
Oh, quantum computing, yeah, sure. So you can buy one today. You can go down to D-Wave and they'll sell you an adiabatic quantum computer. I forgot how many they have, how many qubits they have today, but it's a small number. 8, thank you. And that's a very contested quantum computer. There may not be no entanglement and other things. I have no idea, but let me be honest and say quantum computing will not solve all problems, right? You can't use a quantum computer to solve PDEs. I don't know how to do that, right? It will not run the top 500. And you're going to get approximate answers out. So I think there's a lot of interesting things there, don't get me wrong. I think we should investigate that and develop ideas there and explore that space. It's going to be rich and promises great solution, great advances if we can effectively harness it. Absolutely, yeah. So many problems would benefit. Not all problems though.
What can you say about the trend about the memory bandwidth? So you said there is we see the Moore's law. What about the memory bandwidth?
Okay, so today we have this chip. It has pins and data comes in through the sides of this chip, more or less. And we have computing power, and that power seems to be getting more and more computing power on the chip itself. So the strangle point is in the perimeter, getting data in. We got this area which is doing tremendous computing, so that has to change. So they're working on that. Stack memory, that's here. So today the stack is next to the processor. It's not on the processor, but the next step would be to incorporate 3-dimensional memory on top of the processor itself, so data flows vertically into the processor. Today things are running across a copper line. Let's get rid of the copper. Let's use optic lines to move data. So we get an enhancement, lower power consumption, much greater speeds associated with that. So there's paths to the future which would enhance the ability to better balance those things. But that's going to be that's always been the struggle, balancing communication against operations, and I think it's going to persist in the future as well.
Let's take one last question.
What's the operating system running on the supercomputer? Is it a custom-made operating system or just like standard Linux operating system?
I'm sorry, say it again. What's the
Operating system.
operating system? What do you think?
I don't know.
Linux, of course.
So no customization at all?
So typically what happens is Linux is there. It's a lightweight kernel that's run on each of the processors. And that lightweight kernel does not have all the Linux, doesn't have cron tabs and mail firing up at various times. So all that's been stripped away. So you've got a very basic kernel that's running, which control things. But yeah, it's basically Linux underneath.
Great. And thank you so much.